Hello everyone, today we're going to look at Riemann sums. So we can approximate the area under a curve by using what's called Riemann sums. Now there are several types of them, but we're going to focus on just two. So if I want the area under this curve here, that's y equals 16 minus x squared, and it's from 0 to 4. What we're going to do is we're going to approximate the area, again with what are called Riemann sums. So the first thing that we're going to do is we're going to divide our x-axis into so many segments. So we're dividing this into 4 segments. So we got 1, 2, 3, 4. And then those are the bases of our rectangles that we're going to create. And we're going to create 4 rectangles with the same width, and then the height of the rectangle depends on the type of Riemann sum that we want. So there are things called the lower Riemann sum, which is also called inscribed, the upper Riemann sum, which is called circumscribed. We have the midpoint, the right endpoint, the left endpoint, and basically anywhere within that first, say, from 0 to 1 range. If you pick any point in there and make that the height of the rectangle, that's going to be the type of Riemann sum. We're going to focus on left and right Riemann sums. So I have the 2 pictures drawn here. So in our first one, we have the bases for each of them are the same, right? From 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And then in the left Riemann sum, we're going to look at the endpoints of our rectangle in the y direction. Whichever of those endpoints is on the left, so the lower one, by lower I mean the lower x value, that is the height of the rectangle. So in my second triangle from 1 to 2, I have my endpoint on the left, I have my endpoint on the right, and the height is the one on the left. So again, between these two, I want the one on the left. Between these two, I want the one on the left. So as long as we know our lefts and rights, we'll be able to figure this out. So my right Riemann sum, this one, has, again, the same horizontal parts, or the same horizontal side of my rectangles, but now my heights are going to be the left endpoint. So in my first rectangle, again, those are my 2 endpoints, I want the one on the left. Between this one and this one, I want the one on the left, so that's this one. Right, so it's either the right endpoint or the left endpoint. So from 2 to 3, the right endpoint is this guy. And then from 3 to 4, the right endpoint has a height of 0. So there's no actual rectangle there because the height is the right endpoint, but that's at 0. So again, notice that for each of them, the width of the rectangle is the same, whether it's the left Riemann sum or the right Riemann sum. The width of each rectangle is 1. And then what I'm going to do is now I just have a table of those heights that I had. So again, the x values were 0 through 4. The heights, if I plug in my x values, are the y's. So we get 16, 15, 12, 7, and 0. And if I want the left Riemann sum, again, that's the area of the rectangle. So here is my width. And then these are my heights. And notice we had 4 rectangles, but we have 5 x values, and that's because I need each side of my rectangle. And then for each consecutive 2, again, for the left endpoint, I'm taking the one that's on the left. So I have my 16, and the next 2, I'm taking the one on the left, that's the 15. The next 2 is between 2 and 3, the one on the left is 12. And then between 3 and 4, the one on the left is my 7. If I add those up, multiply by 1, I get 50. The right Riemann sum, we're going to do very similar. For each consecutive x value, say from 0 to 1, I want the one on the right, so I want the 15. From 1 to 2, I want the one on the right, that's the 12. From 2 to 3, the one on the right is 7. And from 3 and 4, the one on the right is 0. So that gives me the 4 heights of the rectangles using a right Riemann sum. Put those together, I get 34. The actual area is somewhere between those 2 values. Okay. if we want a better approximation, because somewhere between 34 and 50 isn't that great of an approximation, we could use more rectangles. Right? The more rectangles I make, the better the approximation under that curve. So for the next one, we're going to approximate the area under this curve, which is the line y equals x, from 0 to 3. So we're going to end it, pretend that's a straight line. I want to find this area. We're going to use both left and right Riemann sums, and we're going to compare to the actual area because this is just a right triangle, and we know how to find the area of a triangle. So we're going to focus on 3 rectangles. So I've divided my x-axis from 0 to 3 into 3 rectangles. So again, I have 4 x values. And I've got 0, 1, 2, and 3. So if I want n rectangles, I'm going to have n plus 1 x values. And then we've got our right and our left sums here, our rectangles. So in my first one, the heights are all the numbers that are on the left. From my right, I have the heights that are on the right. So these are my right endpoints. Again, if I make a table, y equals x, so my x values are my y values. And for the left, my first height is 0. My second height is 1, my third height is 2, because again, those are the points on the left. And again, I have a width of 1, so each distance is 1. So that's my width, my heights are the 0, 1, 2. I get a value of 3. On the right, again, the width is 1. The heights are now 1, 2, and 3. So I get an answer of 6. And again, the correct answer should be somewhere between them. If we look at our pictures again, on my left Riemann sum, the area that I'm counting is what's shaded in blue. And that is clearly not the area under the curve. And I'm missing all of this green here. So this 3 that I have as my answer, that's an underestimate. I know my answer's got to be more than 3. Conversely, in my right, I've got all of this area, and that's too much. I need to take away this area in green. So I know that my right Riemann sum is an overestimate, and that 6 is too much for the actual area. Your answer won't always clearly be an overestimate or an underestimate. We'll see that in a minute. But in this case, they are. But again, I can find the actual area because it's just a rectangle. The area for a rectangle is 1/2 base times height. My height is 3. My base is also 3. So 1/2 times 3 times 3 gives me 4.5, which is between the two overestimates and underestimates that we have. So here's another one. Approximate the area under the curve y equals 1 minus x minus 1 to the 4th using 4 rectangles. And we're going to do a left and a right Riemann sum. So I've got my 4 rectangles. So again, I have, you don't see it because they're zeros, but I have a rectangle here, an endpoint here and here. So I've got my 1, 2, 3, 4 rectangles, and again, my 5 x values. And then I've drawn my left and right Riemann sums. So again, each rectangle's height is the left endpoint's height. So if we notice on the first one, the height is 0 because that's where my left endpoint is at, versus my first one in my right endpoint, my right Riemann sum has a height equivalent to my right endpoint. So again, I've made a table of my values using the formula that we had. For the left, this 1/2 is again the width of each of these rectangles. So these rectangles all have a width of 0.5. And then the heights, again, this first one has a height of 0. This next one has a height of 15/16, then 1, then 15/16. And again, I'm just looking at each pair of values and taking the one on the left. Taking the one on the left, on the left, on the left. And that gives me 23/8. And I'm going to do the same for the right. Again, the width is 1/2, but now the heights, the first one is 5/16. It's the one on the right. The next one is 1. Between the next two, it's the one, on the right. The next one between 1 and 3/2, the one on the right, is my 5/16. And then my last one between 3/2 and 2, the one on the right, is 0. So you're always missing one of the endpoints when you're doing these, because one of them is not going to be the height, because again, you have 4 rectangles, you have 5 points. If I add those up, if you notice, it's the exact same thing, so it's also 23/8. So I can't say my answer is between these two values, because again, this is not the actual area. However, neither of these are necessarily an overestimate or an underestimate. If I look at my left one, my first two are underestimates. My next one is a slightly overestimate, and this one's also an overestimate. So the entire area is not an overestimate or an underestimate. I've got bits of both. And the same is true for the right. My first two are overestimates. I've got extra bits to it. But my second, my third, and my fourth are both underestimates. So you're not always going to have, again, an exact overestimate or an exact underestimate. So I got both 23/8 for both of them. But again, that's not the actual area, even though I got it for both. So let's look at it a little more generically. Suppose we have n rectangles, each of width delta x. So remember, this triangle is the capital Greek letter delta, and it means a change in. Usually we use it to refer to a small change in. So it's a small change in x. X is 1/2, x is 1, x is 1/4, x is 1/8, x is 0.002, some small change in x. So we're going to use some mathematical notation here to write out what we were just doing, the approximate value of the area, which we're going to call A. So A is approximately, and then we've got the summation notation. So remember, this guy is capital sigma. So we got some more Greek letters, and it means the sum. So we're going to add, and we're going to add f of x, x sub I times delta x. So delta x is the width of our rectangle, and our function value, f of x sub I, is the height value. So that subscript I is just telling us two things. One, it is one of our x values, and two, I have n of them. So the part on the bottom says, whoops, let me go back to my marker, says that I starts at 1 and goes to n. So I'm going to have an x sub 1, an x sub 2, an x sub 3, an x sub 4, all the way up to whatever n is. And then that x sub 1, the x sub 2, the x sub 3 is some point in that rectangle. So again, if it's the left endpoint, if it's the right endpoint, if you want to do the midpoint. So it's just the x value, the y value of the x value we're taking. Okay. So again, if it's the left endpoint, then that's what my x's are. If it's the right endpoint, that's where my x's are. So again, it's our rectangle. Delta x is the width, the f value, the y value, that's our height. And then the more rectangles we use, the better the approximation of the area that's under the curve. So the more and more rectangles we use, how do I use the most number of rectangles? That would be letting n go to infinity. So what we have is everyone's favorite limit. And notice also that we have equality here as opposed to approximately. A is equal to the limit as n goes. What we're going to do now is we're going to give this its own special notation. So we're going to see that we've got our limit as n goes to infinity is no longer written. The capital sigma, the summation symbol, has been changed. into this guy here. So this looks like an elongated S because it's coming from the sum or the sigma letter. So it's very purposely looks like an elongated S here. And I'll talk about what the rest of it means in a second. But notice how similar it is. I've got my function, I've got delta x, and now it's written as dx. So that symbol is called the integral symbol. And again, it's an elongated S from summation. So it's called the integral. The a and the b at the bottom and the top of the integral symbol are called the lower and upper bounds. So the lower bound, a, is the one on the lower side of the integral symbol. The upper bound, b, is the upper value. And those are numerical, just like it's alphabetical. So if I'm looking at from x equals 0 to x equals 4, a is 0, b is 4, right? Those are my endpoints. The dx is called a differential, and it should look familiar from our derivative symbols that we used in Leibniz notation before. So it's very much the same thing. This part of the integral is very important because it tells us what the variable under consideration is. So if you've ever got multiple variables, you need to know which one it is that we're looking at. So it's f of x dx. The x is the same. This function, the function itself, the f of x, is called the integrand. Just like the radicand is the thing inside the radical, the integrand is the thing inside the integral. The entire notation is read as the integral from a to b of f of x dx. We need to make sure that we have all of that in there. Something to keep in mind is that the integral symbol and the dx are part of the same thing. Those together make up the integral. I cannot have one without the other. I can't have the integral of f of x and no dx, and I can't have a dx just floating around doing whatever it wants. So they're like bookends. The integral starts with the integral symbol and it ends with the differential. Okay, you have to have them both. Just like in function notation, it doesn't matter which variable we use in the integrand as long as that variable is the differential also. So for example, each of the following integrals are the exact same thing. The integral from 0 to 1 of x plus 2 dx, the integral from 0 to 1 of z plus 2 dz, the integral from 0 to 1 of y plus 2 dy, the integral from 0 to 1 of t plus 2 dt. As long as the variable in the integrand matches the variable in the differential, it's the same. Also, please notice the use of parentheses here. If f of x is more than one term, it must be in parentheses. The entire thing is inside the integral, so you got to make sure that it's in parentheses. So what we're going to do now is instead of asking for the area under the curve, we're going to ask for the integral. But we're going to find it using the Riemann sums because, again, they're the same thing. This integral is the area under the curve. So approximate the following integrals using the right Riemann sum with the indicated number of rectangles, which we're going to call n. So I want to integrate x squared plus 2 over the interval 0 to 4 with my dx. Okay. So again, I can consider this to be the same as what's the area under the curve at y equals x squared plus 2 from 0 to 4 using two rectangles. So again, I'm going to make a table, and we're going to look at cutting up the interval from 0 to 4 into two things. So if I'm looking at the interval 0 to 4, and I want two rectangles, I'm going to need a piece here. That's going to be my third point. And again, if I have n rectangles, I need n plus 1 x values. And I'm just cutting it in half, and halfway between 0 and 4 is 2. So I've got 2 there. And then we fill in the y values. So we've got 2, 6, and 18 when we plug in our x values of 0, 2, and 4. And then I want, and the right Riemann sum. So for every 2, I'm looking for the number on the right. So for my first one, I have 6. For my second one, I have 18. And then the width of our rectangles is 2. We're going from 0 to 2 and then 2 to 4. So the width is 2, the heights are 6 and 18. And that gives us a value of 48. So the approximate integral, the approximate area under the curve, is 48. So let's do the same thing, but now we've got the integral from 3 to 12 of z over z plus 2 dz for n equals 3. So now we're going to approximate this integral, which is the same thing as approximating the area under that curve, from 3 to 12. So I'm going to look at our x values. So we're going to start at 3, we're going to end at 12, and we want 3 rectangles. So we're going to have to split it up into here. So we have our first rectangle, our second rectangle, and our third rectangle. So how do I find these two values? Well, there's a really nice formula for it, and it is just b minus a over n. That is going to be our delta x. That's going to tell us the width of our rectangles. So b minus a over n, remember our lower bound 3 is a, our upper bound 12 is b. So 12 minus 3 over 3 gives me 9 over 3, which is 3. So the width of each of these rectangles is going to be 3. So if I'm starting at 3 and I have a width of 3, my next value must be 6. And then going another 3, I get 9. And then double check it. If I go another 3, do I get the 12? Yes. So that's how we're going to find our x values. Our delta x is going to be, again, b minus a over n. And then we're just going to move that much each time, starting at a and ending at b. So here are 3, 6, 9, 12. And again, we have n is 3, so we have 4 z values in this case. Right? Once again, we have one more than our n. Plugging those into our function, we have our, again, our y values, our f of z values, 3/5, 3/4, 9/11, and 6/7. It's really, really important we don't round here because we're already approximating. We don't want to approximate our approximation. So whenever we can, and we can always do this, assuming you have a calculator or you're good with fractions, do not round at this point. Okay, do not call 9/11 0.9 or 0.99, right? Don't round anything. So just keep the exact full number. Again, you're allowed a calculator, so use it. So again, we want our right Riemann sums. We've got 3 of them. So for each pair, so for 3 and 6, the one on the right is 3/4. For 6 and 9, the one on the right is 9/11. And for 9 and 12, the one on the right is 6/7. And again, that width, that delta x, was the 3. So you got 3 times the 3/4 plus 9/11 plus 6/7. As a full fraction, it's 2241 over 308. It's approximately 7.276, and it's not equal. This is the exact approximation, and this is an approximation of our approximation. Let's do the same thing, but with the left Riemann sum. So here we're going to do the integral from pi over 4 to pi over 2 of sine of theta d theta for n equals to 3. Now remember, it's important to notice that whenever we're doing calculus with trig, it's always in radians, and hopefully that pi over 4 and pi over 2 will remind you that it's in radians. So when you're using your calculator for this, just make sure you're in radian mode. And again, our variable is theta, and we've got d theta here. Okay. So we're going to cut up our interval from pi over 4 to pi over 2, and we want 3 of them. So we're going to cut it into these guys. And again, to find that value, we're going to use that same formula that I talked about, b minus a over n. We have fractions here, so just be careful. So pi over 2 minus pi over 4 over 3. Pi over 2 minus pi over 4 is pi over 4, and then over 3 gives us pi over 12. So our delta x, or delta theta in this case, is pi over 12. So each time we go over, we find our new x value, we're going to add pi over 12 to it. So pi over 4 plus pi over 12 gives us pi over 3. Plus another pi over 12 gives us 5 pi over 12. Plus another pi over 12 does give us pi over 2, which again I know I should have. Okay, so my delta theta, the width of my rectangles, is pi over 12. And then we're going to plug those into our function. And again, at this point, I don't want to round. Okay, so I want sine of pi over 4, I want sine of pi over 3, sine of 5 pi over 12, sine of pi over 2. Sine of pi over 2 is really nice, it's just a 1. But just, again, leave everything. I don't want any decimals in here. Okay, we do that at the end. So we fill in our table exactly. And then we want, again, the left Riemann sum. So here is our width, that pi over 12 I talked about. And again, in my first pair, my first rectangle, the one on the left is sine of pi over 4. For the second one, the one on the left is sine of pi over 3. And for our third, the left is sine of 5 pi over 12. And if you're going to plug this into your calculator, play along, make sure you're closing all of these parentheses so that you're not trying to put signs inside of signs. It's not going to be something nice, right? We've got pi's out there, so our approximation is approximately 0.665. So here's another one, the square root of t dt. We want to approximate that integral from 0 to 100 using four rectangles with, again, the left Riemann sum. So my delta t is b minus a over n. A is 100, A is 0, B is 100, and I'm going to divide by 4. So my delta t, the width of each rectangle, is 25. So when I start finding my 5t values, I'm going to start at 0 and go every 25. So that gives me 0, 25, 50, 75, and at my b, which is 100. Plug it in, and again, I'm going to leave my answers exact. I am going to simplify it. So the square root of 25 is 5, the square root of 50 is 5 root 2, square root of 75, 5 root 3, square root of 110. So again, please, please, please do not round in the middle. You're only making more work for yourself because you have to plug that into the calculator, write down the decimals for each of them, and then when we put it into our formula, I then have to re-put all those decimals in. So you're really creating more work for yourself. Okay. So again, we have our equation here. So again, 25 is that delta t. And then for the ones on the left, I've got my 0, 5, 5 root 2, and 5 root 3. So again, notice that if I'm doing the left or the right sums, I'm adding everything but the opposite one. So the left, I'm adding everything except for the one on the right. If I'm doing the right Riemann sum, I'm adding everything except for the one on the left. Okay. So if I plug all this into my calculator, again, I'm going to approximate here because we've got lovely radicals in there. So 518.283. Notice that we still haven't actually found the area of any of these functions, except for the one that was a triangle, or the values of these integrals, since again they mean the same thing. We've only approximated them using these Riemann sums. So in order to find the actual exact answers, we're going to look at an application first. So suppose we know the velocity of an object at any given time. How could we find how far the object traveled? So if I just know how fast it's going, how can I find out how far it went? If the velocity doesn't change, so it's a constant velocity, then from an elementary physics class we know that distance is velocity times time. However, most things don't move at a constant velocity. So what we're going to do is we're going to suppose that v of t is our velocity function. We're going to look at it at time t, so that's why it's a function of t, v of t. We're going to split the time segment. Say we're interested from t equals a to t equals b, and we're going to split it into n time intervals, each of length delta t. And again, delta t just means a small change in t. So if delta t is small enough, we can assume that the change in velocity is very small, and that it's in fact constant over that, again, very small time frame. So again, we're not finding an exact thing here, we're still approximating, but I'll show you how we get to the exact in a minute. Okay, so we split up the time interval into small segments of time t. We assume over that small interval, a half second, quarter of a second, a millisecond, that the velocity is constant. And that's a fairly nice assumption, again, if delta t is small enough. So over that very small time interval, if we assume velocity is constant, we can use that d equals v times t formula. V would be the velocity at some time in that time interval. So again, that t sub I. And the t, the time, is delta t, the change in the time. Now notice this is the exact same thing we were just doing with our Riemann sums. We've got a function times a small change in that independent variable. So by multiplying two things, I can always think of that as the area of the rectangle. Delta t would again be the width of that rectangle if I wanted to graph out my velocity function, and then the velocity would be the height. So if we want to find, again, the exact distance, we're going to let n go to infinity. And that n going to infinity of that sum of that product is exactly the integral. It's the exact same notation, except instead of f of x and dx, it's v of t and dt. So the distance traveled is the area under the curve, is the integral from a to b of v of t dt in this particular case. So they all mean the same thing. But with this application, there's something I know about velocity, and that is if I want to find the distance traveled and I know velocity, how are those two functions related? Well, velocity is the derivative of position. So if I knew the distance formula or the position formula, I can think of it as the same thing, which we generally call s of t, I can find the distance traveled by just taking the difference of the endpoints, s of b minus s of a. If I know where it is at point A and I know where it is at point B, I just subtract them to find out how far it went. So this gives us that the integral from a to b, v of t dt, which is the distance, is s of b minus s of a, the difference in my distance or position formula. But again, how are those two things related? S prime of t is v of t. So I plug that in, and I get that the integral from a to b of s prime of t dt equals s of b minus s of a. And that is what we're going to be using from here on out. So we're going to look at what's called the second fundamental theorem of calculus. So we're going to replace our s of t's with f of x. And instead of having a derivative inside of the fundamental theorem of calculus, we rewrite it, and we're going to use a capital F, where the derivative of capital F is a lowercase f. Sometimes it's a little confusing because they're both f, but this is generally the way that you'll see it. So it's the integral from a to b of little f of x dx equals capital F of x evaluated from a to b. So remember, this is that evaluated symbol that we use sometimes in the derivative. So f of x evaluated from a to b. And that it's equal to f of b minus f of a. And again, that's f of x evaluated from a to b. And that just means f of b minus f of a. So let's try one example of finding the exact integral value. And again, we're going to focus on this in the next lesson. So let's say we want to integrate from 3 to 7 of 2 dx. So if we graphed this function, we would have a horizontal line at y equals 2, and we'd want it from 3 to 7. Hopefully that it's clear that that is a rectangle and the area is 8. It's got a height of 2 and it's got a width of 4. So the area is 8, and that means that the integral should also be 8 because the integral is the area under the curve. So what we want to do is we want to use the fundamental theorem of calculus. We know that 8 should be capital F of 7 minus capital F of 3, but what is capital F of x? So I want the function whose derivative is my integrand, which is 2. So whose derivative is 2? We go back and we think about the fact that derivative is slope. So we're looking for a function whose slope is 2. So since it's a constant, I know that the function should be a line. And the line has to have the form y equals 2x plus b. Right? And that's coming from y equals mx plus b, everyone's favorite slope-intercept form of a line. So the slope is the derivative, which is 2. So we get y equals 2x plus b. At this point, there is no way to determine the value of b, which again comes from the y-intercept of the line. But luckily, we're going to see it doesn't matter. So if I want capital F of 7 minus capital F of 3, that's going to be 2 times 7 plus b minus 2 times 3 plus b. I'm going to distribute the 2's and the negative signs, combine like terms, and we get 8. So notice the y-intercept value, that b, cancels out in the end. And that's always going to happen. If I have a constant that I don't know of, it's going to cancel out here in these what are called definite integrals. And again, we're going to see that come up again later. So again, we'll go over how to find capital F of x in certain situations in the next few lessons. Again, if the integrand is a constant, then the original function, the capital F of x that we're looking for, is just a line.